Apache Spark is what we are going to discuss. So Apache Spark is a faster version of our normal MapReduce. Along with that, it comes with few nice features that in case of MapReduce, we were only able to do few things. So we wrote map, we wrote reduce, these two functions, and then we handed over our two functions to the mercy of MapReduce. We just handed over our function, our code to MapReduce, and we were on the mercy of MapReduce, and because that will execute it on its own time. Okay, we were not controlling it. Okay, it was just running it. We were just trying to convince MapReduce to run our function when it has time. That was the psyche we carried when we talk about MapReduce. But when we talk about Spark, we are going to control each and every step. We are going to order it. We are going to order it instead of requesting it. We are going to order it step by step. All right, that is the biggest difference. Also, in case of MapReduce, it was only a single phase that has to be can be executed at a one point of time. If we want to combine multiple phases together, say multiple MapReduces, churn this data into this, copy this data file from here to there, and so on. If we had to do all of multiple steps, we would have to take the support of either our local shell script, or we'll have to take a support of, I mean, to combine two set of map reduces together, we'll have to write something called Oozie script, and then Oozie will basically join it together. Or we'll have to write our own shell script, which will do all of this. But that's not the right way of doing it. Okay, because the only medium of communication between two map reduce phase is by the way of HDFS file, and that's not great, right? Because you'll have to convert back and forth, translate the object into file, and then once that is done, then again you load from the file and do that. So two map reduce phases, to combine them together, it is too much of a headache, and there is no other way out, right? So those are the few things which Apache Spark has solved. Okay, now if you guys are not convinced, you will get convinced when you use it a little bit. And so the ecosystem wise, Spark is also quite Apache Spark is also quite powerful. Let me make few notes. Okay, so all right. So at the core of Apache, at the core of Spark, you have something called the Spark, the which we are going to talk about, uh, which has the whole programming language in it. On top of Spark, there are things like Shark, just like Hive. Then there is Spark streaming, which makes it possible to do the real-time processing. And on top of Spark, there is something called machine learning library, MLlib, similar to Mahout. And then there's something called GraphX for processing large graphs. Okay. Now, Spark runs on various kinds of platform. It can run on its own standalone scheduler. It can run on Yarn, which is our Hadoop, and it can run on Mesos. This is the one. Yarn is the one which we are using right away. It's running on our HDFS. All right. So this is the general diagram. Right. In case you want to start using Spark on your own platform, on your own machine or virtual machine, these are few steps. Download Spark from this location. This is good. Okay. Then, because this is the one which runs on Yarn, so this version is designed in that way. And extract it tar xvf, and actually there is going to be something else also. We call it jad xvf. Okay, once that is done, then you move this is optional step, basically moving to some folder and renaming it properly, linking it to another folder, and then launch it. So right now, all, if you got to try it out, you can just run this command and that will be good enough. Okay, user lib spark bin spark. Now this is the Python version which we are going to use. So let me just copy it, and okay, so it comes as a command. All right, so you see this is screen, and then that means that you are on the right place. Okay, now, all right, when it says spark context available as sc, it means that you are at the right place. This is the console of Python, where you can write any of your Python program to I mean Python command, and then check, then run it. Say, for example, this is my Python array, and then I can simply say print a. All right, now this is a proper Python console. In this, Spark has made available one more variable called sc. Okay, sc is the gateway for the Spark context, or the Spark context is the gateway for our Spark. So we'll be dealing with Spark by the way of sc only. Okay, now, all right, now before we move on to hands-on, let's just try to understand few of the concepts which are part of Spark. Okay, few of the concepts which are part of the Spark. First one is resilience distributed dataset. Anything, any data from any place is loaded as resilience distributed dataset. The dataset in Spark, the way we had HDFS, similar to that, Spark went a little bit one step ahead and said that we will define something called resilience distributed dataset, which is essentially a big data set spread over multiple nodes. Okay, resilience dataset, though it's just available to you as a single variable in your program, okay, is basically is the data set which is available across the nodes and is available across the whole cluster. Okay, so although you will be operating on RDD, say RDD, multiply RDD by this, or run this function all over the RDD, you will be doing that kind of thing. But under the hood, that function or whatever modification transformation you do on RD or RDD, it is going to happen across multiple nodes. Okay. Now, RDD can recover from node failures. Okay. Just like HDFS can recover from node failures. And it can have any data type. Has a, basically RDD is a data set which has got the data type like any programming language. Okay, so and basically RDD is the one on which all the operations are done. Okay. RDD has got two kinds of operations. One is called transformation and other is called action. The way we had some paradigm in case of MapReduce, here we have two functions. One is called transformation and other is called action. RDD is more or less like an HDFS. It's just that RDD is sort of RDD is sort of in memory. Okay, and RDD is a temporary one. Okay, it is not something which can be persisted across multiple sessions. We'll talk about this. You'll understand that part. So each element, so RDD has got elements. You can think of RDD as a huge array of objects. Some of these objects are on first node, some of these objects are on second node, while some of the objects are on other nodes. And this object can be further be an array, a complex type, or whatever is possible. Like it could be an object further, it could be array of objects. So you can think of RDD as a huge array of objects, and these objects are available across the cluster. So whenever you apply a function on an object, when you apply a transformation on an object, this transformation is applied, and this transformation, the code that you write inside the transformation is run across the cluster on each object. Okay. So the work is divided onto multiple nodes in the cluster. All right. So is RDD clear to you? It's basically a huge data set. It's a sort of a memory representation of a huge data set. Okay. So you can load, we will be loading our data from HDFS into RDD. When we say loading the data, it only loads a partial amount of data. It doesn't load everything into the memory. Okay, so that's a fairly new concept when we talk about having a data set distributed across the cluster. Okay, and and if you remember the way we had in pig, we said something like, okay, we said something like a equals load from xxx, right? Okay, load from my file, right? So here a is a data set, and this a is just a symbolic representation of our file, right? In the similar fashion, RDD is also a symbolic representation of our file. It but similar to pig, it knows what is the data type of a, right? So it's a similar kind of thing. So I mean, and we will be the way we operate on our this here on A, when we say for each generate, for each of A generate blah blah blah, right? So effectively, if you look at it, we are iterating over our data set and applying some sort of transformation. So exactly in the same fashion, keeping up the same spirit, Spark also let you do the transformation of your RDD and generate another set of RDD. Okay, we'll show you how to do this. So the concept is very likely similar to that one. Like for example, we have got this one. All we got to do is lines equals, you see the lines is the new data set, is the RDD which we are creating. Okay, is the RDD resilience data set we are creating on top of this big text file. Okay, on top of this big text file. Okay, it's loaded, it shows that the lines has got this much of memory, this much of memory. Yes, lines is an RDD. Okay, lines is an RDD, or you can say lines is a part of RDD. Okay? Now, if I have to do something on top of lines, I got to do apply transformation and then run the action. Okay, all right. Say lines dot length, not lines dot length. Okay, I'll show you. Let's hold on for a minute. So we were able to load our big.txt, the standard word count program. This text file, we are able to load into lines. Okay, all right. Now, all right. Now the next step in the game is your transformation. Okay, transformation basically creates a transformation from one data set to another, just like just like our pig script. This is one transformation which generated b from a. All right, we generated b from a. That is the transformation. No. So Pig was using MapReduce internally, but Spark is at its own. Here I'm just using an analogy. While two are very, very different things, Spark and Pig are very different things, but the paradigm seems to be similar one. In both the cases, we create a symbolic data and then we operate upon that data. We always operate upon that data. Any operation you do on a big data is going to run near the data rather than bring near the code. Okay, so the philosophy or the syntax is sort of same. All right, so in a transformation in Spark, also other than RDD, you need to understand there is something called Spark driver application. So there is a computer on which you wrote your code. This is where on this node you wrote your code, and once that is done, you basically sent that program to do your job. So this Spark driver application is the one which is commanding your distributed data set. It sends the transformation. Those transformations are run on this data set, and and you can also tell it to do the cache, or you can also tell to persist a data. You can also tell to persist the data, right? Okay, we'll talk about persist cache later on, but right now you can imagine that this is your code. It is going to ask RDD to do a lot of things, and any transformation you do, that transformation is going to run on multiple node. You can see the multiple times. So each transformation takes the data from RDD and puts it back onto the RDD itself. Okay, so let's do. Why is it old? Yes. So the the transformation is more like a map where whatever mapper you wrote, that mapper ran on each of the node where the data was lying. Okay, so let me just so say wherever the file is lying, if I have to define, first I'm defining a function f. Okay, this is my line, and it basically here I return line length of line. Okay, so I created a function f which basically computes the length of the line. So here it shows me the 7 characters. Okay, and when I give this, it does. All right. Now, if I have to do the same thing on lines, I'll say lines dot map, and will say this is my function. All right. Sorry, this is my new function, which is called line length, lines length. Okay. Now, lines length contains some data. Right now, its length is basically an RDD lying somewhere. If I want to peek into lines length, what I need to do is take 0. Okay. So basically, it shows me, brings the first element from lines length. Here it's second, and so on. All right. All right. So basically, I was able to apply my transformation f. F is given any string, it returns the length. So what I did was on each of the line which was distributed. So our RDD, when I said load the line length, you can imagine that our RDD was sort of an big huge array. Okay, our RDD was big array in which this was my line 1 content, then there was a line 2 content, and so on. Okay, this was our first RDD. Lines is one RDD, you can imagine, and these lines are distributed across multiple computers. Okay, and then we said apply line length on all of these functions. Okay, apply line length on each of these functions, each of these ones. So we said line length equals to, okay, it will become how much? 4, and line length of 2. So this one will become 4 plus 4, 8, and so on. Okay, okay. We applied line length on this and generated this. So this is our new resilience data set. Okay, okay. All right. So that is uh, called line length. Now, once that is done, okay. So you missed that part. So let me just give you this one. So everybody is okay with this kind of model. I think if you have worked on a little bit on pig, you should immediately get it that we are basically applying the you know transformations onto. Okay. Now next step is, now the way we applied a function called map. Okay. All we did was we defined a function called map. Okay. We said here, when we're talking about, we said LL equals to this, which means LL equals to this. And what is our F? We had defined our F as some func variable, and we said return length of line. Sounds good to you guys? So this is how we define a function. This is how we define a function on Python, okay, and this function is being applied on each of the lines. And when you apply using a map, you know, lines is the resilience dataset provided by Spark, which has a function called map. This is provided by Spark, remember that. And when we apply any function via map, this function will be made available each line out of these lines, each object which are part of the resilience dataset. So everybody comfortable with this? No? So only Anna is comfortable. Abhishek, okay, okay. What did I do? Okay, okay. All right. Where are the other people? There were probably 10 people. Okay, good, good. So, so we applied a function via map. So map is one of the transformations which basically the map is one transformation function which let us apply our own logic on top of the data. All right. So similar to map, there are other transformations which are provided by Spark. Okay. The other one is filter. Filter will give us the result. So if we say my filtered filtered records, okay, or lines with first capital, okay, will be equal to, we can say lines dot filter and my function. And when we define this my func, we say lines, and then we can write anything with if we, whatever we want. If lines sorry line dot zero, okay, is greater than a, and lines 0 less than equal to z, right? Now return true, return false. So what am I doing here? I defined a function here. Can you see my screen now? I press some button. There is an arrow button. Okay. Yeah. So what I did while you could not see the screen was this. All right. What I did was I wrote a new function called myfunc. Okay. I said if my line is greater than line, the first character of my line is capital A or or less than equal to capital Z, return true, otherwise return false. This is what I said, which means, and then I said lines dot filter, filter my lines based on this function. So only those records or those lines will be retained in my output. This will be a new data set which will contain only those lines which has the first character as capital. Okay, so so filter is another kind of transformation provided by Spark. First one was map. Map does the in play, not in place. Map does the transformation of your RDD. Filter Filter will only let the elements from RDD go to the next RDD based on certain function, which basically tells true or false. And okay, so in case the function returns true, the record goes through. Okay, so in case of filter, for each of the records on your RDD, your function is going to be applied. In case your function says true, that record will reach the output. Otherwise, that record will be dropped, and that is how it goes. Okay. Now, okay. So this way you can do the filtering and the where clause. Actually, I missed few questions, so let me just. Is Spark widely used in industry? So yes, Spark is picking up. Spark is picking up very fast, and I mean, I like this as a paradigm because it puts you in a complete control. You are not at the mercy of Hadoop MapReduce to execute only one map or one reduce at a time. Okay, if it returns other data types, the return data type will go to the file. It's not going to the file, but it is going to this new form of the RDD, the new created RDD, right? So that is the filter kind of transformation. Then there is a nice transformation called filter map. Filter map is exactly like your normal map reduces map, where each item, in case of a map, you must have noticed, in case of a map, you must have noticed that there could be only one transformation at a time. Okay, there could be only one transformation at a time, meaning one input record in RDD can only result in one output record. One input record cannot lead to multiple output records. That was the map. But in flat map, the beauty is it lets you generate multiple outputs. Okay, it lets you generate multiple outputs for each of these records. Okay, so yeah, so so Abhishek's question is that he's not able to visualize how Spark acts an alternative to MapReduce. Basically, in case, I mean, although it's actually a difficult thing, but you can take a parallel between Pig and Spark. Okay, that will be easier. So these are the few transformations. Now, then after the transformation, you have got actions. Okay, after the transformations, you have got actions. Actions is something which brings the data from RDD to back to your node on which you are working. If you notice, then here we are not able to, if you take lines is an RDD, and to bring lines back to a single node, you need to apply an action. Right now, lines is distributed across the cluster. Or if you want to find the summation of all line lengths, then you got to apply a transformation, because line lengths, our line lengths, okay, is right now distributed across cluster. If I have to find out lengths of, if I have to find the summation of all the numbers, then we will have to apply a reduce function. So all the transformation did was created another RDD out of an existing RDD. That's what the transformations did. Transformation was of type map, filter, flat map, this, that, right? While our action is sort of a summary which brings sort of, say dump. You remember in pig when we said dump, that's when we got our data output. Similarly, when we said store, only then it triggered pig to bring the data here or store somewhere. Okay, action is exactly same thing. Action is something which forces the uh, spark to take some actions. Map is sort of, I have noted down that you want to do this transformation, but I will do all of this transformation the moment you execute your action function. Okay, so that's how the spark works. So so transformation is mostly like, we said, you said it, I noted it, I'll do it when you execute an action. That's how it behaves. Exactly the way pig also did. We told pig to do for each, do this, do that, until we said store or dump. It didn't do anything. Okay. So if we have to find total length, so what will we do? First, first, say we want to find out summation of all this array. Okay. We have got line lengths. Line lengths. Let me take the actual variable here. Okay, so we got line lengths. Now we want to find the summation of all the lines. All right, now what we got to do is, first we define a function, define my summation, okay, and line length, and then I say return, let me call summation of a comma b is return a plus b. All right, that's the summation. So let me define my summation. Good. Now if I can quickly test, beauty is I can quickly test whether my function works or not by doing this, right? So this is normal normal Python. Okay, this is normal Python where I can even say this, not this, we can reuse it like a calculator. So I defined a function called summation which basically adds up two values. Now I said lines length, okay, and then I said reduce. Reduce is the most important action provided by, now val equals this. Okay, now if you see the value has given me total lengths of the whole file. Yes. So yes, we wherever we want to keep this data, we can keep this data just like pig, because now we are inside our Python, and SC also provide the Spark context, that object inside Python also lets you save a file to a disk the way it let you load a file. All right, sounds cool to you? So that was action. And action here, right now we used action called reduce, to which we passed a function. Okay. Now there are few important things you need to note is, all right, and also if you just want to collect all the variables back, what you're going to do is you say collect. Now all of these values are going to go from multiple nodes to a single node. Okay. So we are going to get all my vals as a normal array. You can see this use array. It has been collected from across the node. to a now printable format, which is normal Python variable, right? So take is something takes the data, collect is something collects the data from all across nodes and brings it back to your launcher place from where you started your Spark, or we call it application, we call it Spark driver application. Okay, it basically actions make it possible to take the values from whole RDD onto a single place. Okay, that is another action. Here we were talking about the reduce function. Reduce function is more like reduce function is more like your combiner function. You remember combiner? Anybody remember combiner? Do you remember combiner function of MapReduce? No. Okay, Vishnu remembers combiner. So this reduce is little different from MapReduce, because in MapReduce the function could take multiple values. All the values for a key were made available to the reduce in a single shot. Here, two values at a time are only provided as as the argument. You saw our function here. Here we just did summation of two values. Okay, we said sum only two values, but just now I demonstrated to you that we were able to do the summation of thousands of values. Okay, we were able to do the summation of thousands of values, right? Now how does Spark do it? Spark basically takes two values at a time and then sums them up or applies your reduce function, then takes another two values and applies it all over, and then it keeps on taking consuming two values and converting into one until everything is done. Okay, until everything is done. So all right, so basically it does sort of just like combiner, it takes two values at a time, converts it into one, and can anybody tell me if we have got, just a second, let me make it. Okay, now you can see Anna. All right, now my point here is that we are taking two values at a time and applying, which means only few functions are eligible to do this kind of job. Okay, and not every function is allowed to do can be allowed here. Okay, now let me take an example, because this is something you will struggle most with. So let's say I want to find average of values. Okay, I want to find average a comma, or let me first try to demonstrate to you summation. Let's say my array is 1 5 7 8 4 and 20 10. Okay, this is my array, right? Now I want to do an average. Okay, average of values. So I wrote a function which essentially re- returns me, all right, which essentially gives me the average of two values. Now I want to reduce. First I will load sc dot parallelize. So in case you are just loading any variable instead of from HDFS, okay, we'll say, okay, b equals a dot reduce, and I say average. Okay, what am I saying here? apply average function on two values at a time. It will apply on these two values, then these two values, and these two values. After this, there will be three values, and then the whole process will follow just like a tree. So, can somebody tell me if we have n records in this array, how many times in total the reduce function is going to be applied? In this case, 1, 2, 3, and then we'll have three values left after this, and then it'll go on. No. Is anybody agreeing with Anna? Yes. So next time it will be n by 4. So n by 2 plus n by 4, okay, and then n by 8 and so on till the overall value reduces to 1. Okay. So it will be something like n log n. Mhm. All right. So do you think it will give you a good results? Is this correct? Or let me put this way. If so, the average of this one is how much? Yes, we are just expecting one value. I'll show you. So let's just parallelize this. All right. Now we have got A as RDD. Let me define this average function. Test this average function. Can you see the beauty of it? I could test it very immediately. You see 3.5, right? And now I apply this average function. Now let me see what comes out. It says 3.75, right? Ideally it should have been how much? It should have been this divided by 3.0, right? Okay, so all it did was first it did 1 plus 5 divided by 2.0 divided by 2.0. Now whatever came out, then it added it with 8. Okay, or it must have done it in another manner, and every time you'll get a different set of results. Okay, it's very difficult to predict which way it did. Okay, so yeah, I think this is the way it did. It first added the last two, then whatever result came in, it added it with 1 and then divide by 2. Okay, so is everybody okay with this? So basically, average is a bad way to do average this way. Can somebody suggest me what will be the correct way of doing average in a parallel manner? Anyone? If I have to find average of n values using this reduce function, what is it that I'm going to do? Yes. So first we will basically reduce using summation, and whatever output comes in, we will do count. So we'll say define sum, let's call it sum a plus b, and we'll say return a, not a plus b. We have this, we say return a plus b. It will return the summation of two values. And what are we going to do is we say sum equals a dot reduce sm, we'll got sum, and then we say count equals a dot count. So both reduce and count are distributed. Count is going to go to each node and ask it that, hey, how many elements do you have? And then sum all the counts from all the nodes. So effectively, these two values we will get, and our average is going to be sum divided by count. Okay. All right. So you can also write your root mean square value in the same way. Okay. You can also do your root mean. Ideally, the root mean square value is square root of a plus b, a to the power 2. So if you have got, okay, so this is your root mean square value, right? If you have to find this, okay, if you have to find this, you'll have to find this part in a distributed fashion and then divide by under root 2. Yes. So, yes, that is the purpose, Malik. So, the objective is that not a single load should not be loaded with your work. The work should be divided then and there. Instead of transmitting the whole data to a single node and then you summing it up, you would be transmitting only a small number from all the nodes. So we did two things by using these reduce function and count. We did two things. Okay, why didn't we just say, there could be other way, right? We could have said my array and we say a dot collect, right? We say a dot collect and then we got an array, and now we can run our average function. Okay, summation of my array divided by my array dot length, right? We could have done this. All we did was we requested all nodes to give us an array. We brought all the data to a single place, and then we found the summation of this whole array and divided it by length, and we got an average, right? This is local. This is our local way of doing it. Okay. In this, there is no distributed computing. Okay, it's a single node doing everything, and we're bringing all the data to a single place. So what it does, this approach and the approach above has got two different objectives, two different uh, dynamics. The approach above first utilizes all the computers to do the work. Second, this approach has a very minimal data transfer. Here the data transfer is only two numbers, okay, or maybe 10 numbers, or maybe 20 numbers. Basically reduce will take summation from all the nodes, one number from all the nodes. Same is the case of the count. So if you have got n nodes, total number of transfers will be 2n, 2n integers, which is going to take you a millisecond of time. while the above one is going to take you, depending on the data, a humongous time. If you got a terabyte of data and you are doing a summation on that, this approach might give you the result in few seconds, while this approach can take hours. Okay, this approach is seconds and this approach is hours, and now you can understand the difference, right? Second, you have distributed computing on also from the point of disk reads. You got so many disks parallelly reading the data and doing your job. Okay. Third is, if your data is too big, if your data is too big, if your data is too big, say it is not fitting into RAM, then this approach is stupid. This will not work. If your data is bigger than the RAM, you are trying to do summation of few hundred GBs, then this approach is not good. All right. All right. So having said that, the most important thing to note is this is right way and this is wrong way. Okay. The most important thing to note is that when you are writing your Spark, that is the only biggest downside of Spark. You might end up doing this silently and you would not even realize that you are actually doing things wrong way. Okay. And this is probably one of the important questions I generally ask in interviews, that given this algorithm, given this particular program, Spark program, do you realize that you have made a mistake? Do you think this is wrong? If this is wrong, can you make it right? Okay. So everybody convinced, everybody is with me in this. Why this is wrong, another is right. One is local, other is distributed. Parallelize actually takes your local variable and makes a RDD out of a local variable. It's just opposite of collect. Collect brought the data from RDD to local variable. Parallelize took the local variable to the RDD. Yes. So the why it's wrong, because we basically did not utilize any of the Spark's features. We said to Spark, hey, give me the data, I will do my job, right? Instead of distributing computing, you did the local computing. Yes, you are right, Anna. So good. Yes. Excellent. Excellent. All right. So this is local, okay, and this is distributed. Sounds good? Rumen? All right. All right. Okay. So please explain about RAM and data. Yeah. So all of these are variables in the RAM. Okay. So the RDD is basically disk supported very well, but lot of processing, it basically Spark utilizes as much RAM as possible, and it is actually possible to spill over to the disk. Okay. All right. Now let me. hmm, These are very good questions. But since we have got multiple computers containing a bigger RAM, we could utilize it distributedly. Right? Now, you could utilize the RAM of multiple computers parallelly. Right? So that is one thing. How do we take a call to use Spark or MapReduce? If you have to write a code, if you have to write a code, basically which involves multiple steps, multiple MapReduces, Spark would be a better take. Okay, all right. The same thing what we discussed has been explained here. We did a line length computation, and this one, if you do straight away, it is going to be 62. And now this RDD, this we converted into RDD. Some data on node 1, some data on node 2, some data on node 3. Okay, and this is our driver node is the one from which we launched our script, and this is our RDD distributed across. Now now here we did a line length, okay, for each one, and the summation was this. So each node computed the summation, its own summation, and on the driver node, when we did summation, these three variables are transferred to the driver node, and then the summation happens again till we reach to 62. Okay. Now I hope that whole cumulative reduce function is clear, and where it's valid and where it's not. Right. Now, Spark comes up with something called broadcast variables. Broadcast variables are really nice in the sense that basically what in case of a broadcast variable, we we make it possible for each of the node, each of the RDD to broadcast. Okay, when we have our Spark application, our function running on each of the RDD segment across the cluster, can they communicate? Everybody has this question that when I'm running my work on multiple nodes, can they in any way communicate with each other, right? This was a common requirement in case of Hadoop. That is why the broadcast variables were created. Broadcast variables make it possible to for various Spark applications to communicate with each other. They can broadcast something and other people can read from it. Okay. So you can broadcast saying s dot broadcast and this. Alright. So we can say sc dot broadcast and 1 comma 2 comma 3. All right. um, okay, so x is the one which is my broadcast variable. If you say x, it tells you that it's a broadcast object, and to get the value you always use value. All right, you always use x dot value rather than manipulating it. Okay, so this way the value can be broadcasted to all the nodes, and every node can read from it. Alright. Now, so one was broadcasting things, other was say all the nodes are sending you, all the nodes want to give you some data continuously. They want to keep on giving you the data continuously. Do you guys remember, any of you know what is a static variable? I'm asking about static variable in Java or C. Right. So no matter how many times a function is called, this static variable keeps on increasing, right? And and in case you have to do the same thing across the nodes, across the Spark RDD, if there are multiple nodes counting lines, so that number should be, we should know the summation rather than only this one. So in those cases, Spark has come up with something called accumulator. Each application keeps on accumulating it. Okay. In case of static variable, they could also decrease the value, increase the value, and assign the value. Here, Spark application can only inform you that hey, I am a plus 10. Okay. They can only give you a new value. They can only keep on appending to the value. They cannot change the value. Right? They cannot say alter the by choice. Okay. And why is it so? Because if they want to increase or decrease it, there will be race conditions. Okay. Why? Because it's like a pipeline. All of the values are flowing. It's a unidirectional pipeline where all the values are flowing from Spark application to the accumulator. Okay, sounds good. And these accumulators are good if we are talking about associative operation, meaning the order in which the values are received is irrelevant. Okay, if a Spark application says that 2, first says 2, other says 3, other says 4, and this thing is happening, uh, only addition is happening, then overall result is going to be same, no matter the value is received from first node before then the node value is received. No matter where the whether values from node 1, node 2, node 3 are ordered, unordered, in which order did we receive the values from these nodes. So accumulators are the cool thing, just that they can only be good for associative thing. Like for example, if we have only associative operation, we say 2 plus 3. So we have plus 2 came first, then plus 4, and and our result is how much? 2 plus 3 plus 4 is 9, right? Now, in case we had 2 plus 2 into 3 minus 4, right? Now the results will be very, very different depending on how it comes. Okay, this is 2, but if plus 2 comes uh, plus 2 minus 4 into 3, if this is the case, then you got, what did you get is minus 10, right? While no matter 2 comes first or 3 comes first, it doesn't matter here. It will always be 9, right? So that is the thing. That is the deal with the associative functions. So 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 it's generally this associative function. You can't do beyond it. These are simply accumulators, right? So here we are trying to do the word count. Okay. Let me also, here I have written it in Scala. No, it's actually Python. Let me write it in a neat fashion. Okay, so this is a standard word count example. Okay, you need to be with me when I talk about this. Let me simplify it. Okay, let me simplify it. So first, here in this example, we imported a regular expression that is a library of Python. Okay, let's just import it. Good. And then we loaded our big text file, the one which we used earlier, into an RDD called lines. Now what we are going to do is we are going to do a flat map. Okay. Flat map basically generates multiple lines for one particular line. Here lambda function is like anonymous function. We have not defined a function earlier. Here we are just defining it now. Okay, it is equivalent to saying define is split, and these are line. Okay, and then we say return line dot split. Okay, split based on space. So okay, let's just see how is it working or not. It is very important to understand it right away rather than later on. Okay, so it's working fine. Now once we have splitted it, we just did a flat map split, done. Actually we should give it some other name, because it will confuse with. Okay, now no, there is no constraint for the keywords. Now once we have fm, just to take you know, so you can see I just took 10 variables. It has created a big array. If you can see, it's a big array of words now. All right, it's a big array of words now. All right, now what we could do is we have splitted it. Now the next one is we essentially are cleaning it up, removing all the variables, or all the special characters from it, and then converting it to key value pairs. So let me just, okay, I'll just undo a little bit because I don't like this lambda function with respect to syntax. Okay, let me say, okay, I say my map function is that. So if I say Okay, or for time being, let's just say that we all we want is return word dot lower comma 1. Okay, that's what we want. Okay, and then I say the next step is I take, right, now m dot collect, not collect, we say take 10 just for testing, the way we do tail when we are dealing with a big file. I'm doing take, so just to sample what is there. Unicode object is not of the type this. All right, now there is something wrong with this, so mp, this is correct only. Okay, so this bracket is for who? So here I close my sub, this one close my sub, then close the lower, then closed this. I think this is wrong. All right, yeah. So now if I say, so sub takes at least 3 arguments. Let me just remove all of this. Okay, so now I'm able to generate key value pairs. Basically it was a problem with the regex function. Right. So all I did was for each of the word in my input, I generated word followed by one, key comma one, key comma one. That's all. Now the next step is to do a reduce. Reduce is nothing but I'm saying summation. I'm just sending the summation function for the reduce by key. Okay. So now we have got counts, and counts dot take, accounts dot collect, accounts dot, let's say take 10, because this is counts is going to be big. See, so now we are able to find out the counts here. So you can see that. Okay, now to save it to the text file, you can simply say this. Okay, you can simply say this file already exists. Let me just put 6 December. All right, so it is saved onto this place. You can check this place. We can see, say Hadoop. Okay, we can say Hadoop fs minus tail, and you can see this. You can see that there were two reducers. It did something. It saved the result somewhere. See, this is generated by Spark for you. Okay, this is generated by Spark for you. Just to see if it is doing good job, what you can do is you can say part dash 1 2 3 4 5. And here we go. So here you can see we have been able to successfully generate the word count, and that's pretty much okay. Here here is the same form, same example in a different form where I have taken out lambda functions and tried to convert that lambda into little more readable format. And yeah, and also you can have a look at the accumulators over here. This is how you do the accumulators, and their broadcast is also an example here. You can broadcast all across. Okay, this one you are talking about these few ones. So okay, so I'll just share it as a rough notebook, and we will put it. I'll not put it in the slides, but I'll put it on LMS. All right, Anna. Okay. So that's pretty much. We will continue with the Spark streaming a little bit. Okay, and after that we will. First, tomorrow we are going to. So Python reference material. Actually, Python's basic tutorial is actually pretty good. Okay, and yeah, Python's basic tutorial would be actually more than sufficient. I'll put it on LMS, okay, in a separate file. No, lambda cannot be a undefined function. You should have a look at little bit of lambda syntax. Lambda syntax is little tricky. Okay, lambda syntax is little tricky. Lambda is like anonymous function. Okay, lambda, lambda. Okay. Oh, you are saying lambda is a user-defined function. No, actually, lambda is a syntax for anonymous function. Okay. If you here, basically, we defined a function without saying define my function. We just wrote our logic right away. That is lambda. All right. Lambda comes from Lisp. In Lisp, we had this lambda mathematics, and lambda mathematics was a probably pretty old computing way. Python's basic tutorial, the one which I like was Python tutorial. It was on their own website. I like that one. This is the one. Here, this one is actually quite simple. It'll take maybe few hours, and it should just go good. Here it'll start with this one. Okay, and actually you should just, I mean, the reason why I started using Python more and more, I started using Python as a calculator. I kept on doing computation on this. Okay, we could do multiply. Okay, and then I started assigning variables to things, and then uh, okay, and then started using it, and after that we started functions, and then defining things, then maybe loops, then maybe loops. All right, so that's pretty much. So actually, the thing is, you could also use Java, but the Java shell is not available. The way I was able to demonstrate to you everything so fast, and we could get a kick out of it, that is not possible if you're using Java. That's the reason I've kept it to Python. Because had I been using Java for each and everything, I would be compiling things, saving it into the disk, and then uploading it somewhere, then running it. It'll be too big too big a cycle. Okay, although Python is fairly possible, but sorry, Java is fairly possible, but not this. All right. Good, good. So here, this is an example of using broadcast and accumulator. Go through this example in the PPT. It is there. And let me just export the PPT so that it is synced. So any other questions? And we will see you next tomorrow. And we will talk about Oozie and Spark streaming and project and comparing NoSQLs. Okay. All right. Thank you, Abhishek. Thank you, guys. Thank you, Ruman. Thank you, Vishnu. Tomorrow is our last session. Yes. Thank you, Malik. Have a great day.